Okay, so welcome everyone to the Math Colloquium at IISERM-Maths, and today we have Professor Narayanan from IISc Bangalore, and he'll talk on Toplitz operators on quotient domains. So, over to you.
Okay, so thank you. So first of all, sorry for the wrong spelling. I hope that is correct now. Okay, so thank you very much for the invitation, and I'll talk about Toplitz operators on quotient domains. This is joint work with Gargi Ghosh, who's a postdoc here. So I'll start with a very general introduction to Toplitz operators, tell you some results, and then bring in what are known as pseudo reflection groups. And then we move on to the quotient domains, and then I'll present the result. Okay, so well, I've taken the simplest approach in the sense that I'll tell you only things which are very simple. Of course, most of the things I do are very simple, but instead of complicating things with notation and so on, I'll stick to the simplest possible cases always. And feel free to stop and ask questions. Okay. So what are Toplitz operators? So let me start with the definition. So we'll look at the Harmonic space on the unit disk. So this is actually a function space defined on the circle. You look at all those functions, summation a n z to the n, with summation mod a n square is finite. So that's actually contained in L2 of the circle. Okay, so Harmonic space sort of lives on the circle in some sense. And since it's a closed subspace of L2 of t, you have a orthogonal projection from L2 of t to H2. And if I take a bounded function on the circle, the Toplitz operator t sub u is you take a function in the Hardy space, multiply by u. Now u is a bounded function, so it's no more no more necessary that uf is in the Hardy space, but you project it back. Okay. So this is actually an well, you can write it down more explicitly than this. This is actually an integral operator. Integral operator because the Hardy space is a reproducing kernel Hilbert space, and so projection is given by integrating against a reproducing kernel. Okay.
First line is not clear to me. At H2D, you are taking a function on unit disk, right?
Well, H2D you can think of as holomorphic functions on the unit disk whose boundary values are in L2 of the circle.
Okay.
Okay. So if I have summation mod a n square is finite, summation a n z to the n will be holomorphic in the disk.
Yes.
Okay, but it essentially lives on the circle. Okay, so there is a difference. We will see some other spaces too. Okay. Now this Toplitz operator, because the projection is an integral operator, the Toplitz operator can also be written as an integral operator. And there are two lines of investigation, roughly speaking. One takes up. One is the operator theoretic properties of Toplitz operators. Other is because it's an integral operator, one can ask about boundedness on LP and so on, regularity properties and so on. Which is more of harmonic analysis kind of problems. Okay, even though I claim to be a harmonic analyst, I will stick to the operator theory part of this. Okay, so let us go ahead. So this is Toplitz operators on Hardy space. Okay. So Brown and Halmos initiated the study of Toplitz operators long back, and one of the main theorems, so I'll not get into all the results proved by Brown and Halmos in their paper, whatever is needed for our talk. Okay. So one of the main theorems. Question? Any question?
No, there is a question.
Yeah.
Some noise.
Yeah. So well, one of the main theorems is by Brown and Halmos is that if you take two Toplitz operators, so remember TU is simply the projection to the hard disk space after multiplication by U. TUTV is equal to TUV. So this is one of the problems, or well, makes the topic somewhat interesting, that it's not a multiplicative map. U going to T sub U is not multiplicative. And they find, Brown and Halmos find a necessary and sufficient condition for it to be multiplicative. TUTV equal to TUV if and only if either U bar or V is in H infinity. So H infinity means bounded holomorphic functions. So U and V should be the boundary values of bounded holomorphic functions in the disk. Okay, so remember U bar and V. So U is the first element. Okay, so TUTV equal to TU. Now, as a consequence of this, one of the important consequences of this is the zero product theorem. There are no zero divisors here. That means if the product of TU and TV, so these are Toplitz operators, if the product is zero, then one of them has to be zero. Either U or V is identically zero. Okay, so well, I'm not going to get into the proofs of this, but the conclusion is, so this is the problem we will focus on for this talk, the zero product theorem. There are other questions from Brown and Halmos which comes up with which people have studied, and we have some results, but we will not be talking about that. Okay, so I'll essentially stick to zero product theorem because it's much easier to explain this. So question is, if I have Toplitz operators, product is zero, can you say the one of the symbols? So this U, V are called symbols of the Toplitz operators. Whether can you say the symbol is same? Okay, and Brown and Halmos initiated the study which said that it is true on the hard disk space. Okay, so Halmos also asked a general question whether if you take finitely many of these functions UJs, let's say bounded function, and look at the corresponding Toplitz operators and the product is zero, then can you say one of the UJs should be zero? So yes, and it was proved by Aleman and Vukotic as recently as 2009, even though the problem was raised maybe late 60s or early 70s by Halmos. And even the proof in the case of hard disk space requires certain really new ideas which says that the problem was actually quite difficult. Okay, so we go ahead. So from the hard disk space, we go to the Bergman space. So Bergman space is L2 holomorphic functions, essentially. Okay, whatever domain you are looking at, Bergman space simply means L2 holomorphic functions on that domain. So here we look at the unit disk again. You have L2 of D with the usual Lebesgue measure, and A2 of D, that is the Bergman space, that consists of holomorphic functions in L2 of D. And you have the Bergman projection P. So I'm going to use P for all these projections. Strictly speaking, one should put some suffix to say that these are different projections. But since we are not going to use any explicit formula anywhere, let's hope there is no confusion. And just like what I mentioned about the hard disk space, the A2D, the Bergman space, is also a reproducing kernel Hilbert space. And so the projection is an integral operator, and TUF, the Toplitz operator here, is also an integral operator. Okay, one can write it down explicitly. And one can ask the same kind of questions here. And this was taken up by Ahern and Kukovic in 2001, and then it was continued by Ahern in 2004, the zero product theorem, right? So if I have two Toplitz operators whose product is zero, can you say the symbols are zero? One of the symbols is zero. So now notice the difference between the theorems of Brown and Halmos and this result by Ahern and Kukovic, that if here you need, see now the space A to D lives on the disk D, right? There is a domain. The other thing was a circle. Here you have an open set D. Holomorphic functions in open set is what we are looking at. So if U and V are bounded harmonic functions, now that is a strong condition on U and V. In Helmholtz-Brown, you had only L infinity functions. But remember that it was on the circle, and you know that any bounded function or any reasonable function, the circle has a harmonic extension. Okay, so that is what is showing up here in some sense. If U and V are bounded harmonic functions, you can slightly weaken the hypothesis. Ahern's result actually says that, but I'll not get into it. If U and V are bounded harmonic functions and you have a zero product, then one of the symbols should be zero. Okay, so either U or V should be zero. Now, remember the question of Helmholtz for the Hardy space. If I take finitely many of the Toplitz operators and take the product, and if that is zero, can you say one of the symbols is zero? That is still open in A2D. Well, it's even for two symbols, right? TU, TV equal to 0 when U and V are simply bounded functions. That is still open for A2. Okay, so
here also
is
there a formula? Naru, is there a formula for TU, TV like TUV for some U and V?
Yes. So it's okay. So there are results which will tell you when TU, TV equal to TUV under some conditions. Is that what you're asking, or?
Yeah, that's what I'm asking.
Yes, yeah. So there are results of that kind. There are results of results when they commute. For example, TU, TV equal to TV, TU. There are results when TU is compact operator and so on. On the Hardy space, there are no compact Toplitz operators, but for the unit disk, if the Berezin transform of the symbol goes to 0 on the boundary, then it is a compact operator. So there are quite a lot of, this is a huge industry. So I'm just telling you what I know, and in fact a very little of what the whole thing is about. Okay, so keep in mind that there is a huge difference between the Hardy space and the Bergman space. You need the condition that U and V are bounded harmonic functions for zero product theorem. At least this is all is proved. Okay.
And for the Hardy space, could you recall what is the conditions on U and V?
So here there are no conditions. U and V are L infinity functions.
Just L infinity.
Yeah. Okay. But see, any L infinity, because it lives on the circle, right? So any L infinity function on the circle has a harmonic extension. So that is what sort of shows up here. Once you go to the Bergman space, you need the whole domain, not the circle alone, right? Okay.
So when you say harmonic extension in the terms of the Poisson.
Yes, yeah, the Poisson. Yeah. Okay, so now we jump to higher dimensional cases. Let omega be a bounded domain in CD. So the two domains we will, you can keep in mind are the classical domains. One is the polydisc, so this is the notation we will use, and the unit ball in CD are the important example one generally studies, the spaces on these. So Bergman spaces on these domains, L2 holomorphic functions on Dn and V. And if you take a domain, omega, bounded domain, Bergman space is, of course, the closed subspace of holomorphic functions in L2 of omega, and you have this orthogonal projection again, and you can define the Toplitz operators, right? So just like what we did earlier, you look at a L infinity function on omega and multiply f, which is a holomorphic function on omega, which is in L2, and then project it back to A2. Okay, so that is your Toplitz operator, and we are interested in Toplitz operators of this kind on quotient domains, which will come to later. So instead of looking at just omega, you can L2 of omega, you can also put a weight. Okay, so I'll not talk about this. Our results cover such cases, but we'll not, in this talk, we'll not look at that. You can put an appropriate weight on omega, for example, a strictly positive continuous function, and then all the statements will be still true that the holomorphic functions will form a closed subspace and you have a orthogonal projection and things like that, and you can define the Toplitz operators in general. Okay. So let me tell you some results about higher dimensional cases and then go to quotient domains. So, so this is not too well, somewhat recent, I would say. Cho, Ku, and Lee, Korean mathematicians, proved a zero product. So, as I said, I'll stick to the zero product theorems for Toplitz operators on various domains, right? So, these three people proved the zero product theorem for the Polydisc, but again, you can see how the conditions are changing. For the hard disk space, there was no condition. You simply needed bounded functions. For the unit disk, you needed bounded harmonic functions. So, of course, that is one expectation, that you will have some kind of harmonicity coming in, and that you can see in the theorem. Suppose U and V are bounded D-harmonic functions. So what is a D-harmonic function? This simply means that it is a harmonic function in each coordinate. Okay, so U is D-harmonic. So remember, it's a function on CD, right? DD, our domain is D to the D, so that is inside CD. So D-harmonic if in each variable, right? So you look at the Laplacian in each variable. So let's say Zj, dZj bound, right? So that is the Laplacian in the jth coordinate, and this should be 0. Okay, for every j, right? That is your D-harmonic function. And if you have a bounded D-harmonic function, but there is an extra assumption that it is continuous on, of course, it's continuous on in the open set DD and continuous up to the boundary. Okay, some part of the boundary. Well, not the whole boundary, topological boundary, but this is actually called the slow boundary. But simply look at the circle cross circle cross circle D times, and you have a relatively open set W, and your functions are continuous there. Then the zero product theorem is true. So that's an extra condition needed. Okay, so some of this, I don't know if it is possible to get rid of such things. There are differences between one variable and several variable complex analysis, and some of these differences sort of creep in. So the theorem says that if U with TV equal to 0, then either U is 0 or V is 0. Provided they are bounded D-harmonic functions and continuous on some slightly bigger space, right? So the W is a relatively open subset of the slow boundary. And you have similar results for the unit ball VD also. I'll not write, I'm not including that. It's by the same people, or perhaps there is one more author in there. So these are some results on the disk and the higher dimension. Okay. Now, time to define quotient domains and so on. It requires pseudo reflection groups. So pseudo reflections are slightly
goes up to the previous page.
Previous slide. Okay.
Okay.
Just one question, that instead of this bounded domain, if we take the whole complex and define pocket spaces, then the zero product theorem can one expect?
Yes, so there are results of that kind. So people study Toplitz operators on various domains, not just bounded domains. You can look at the whole complex plane or CN, and you can put the Gaussian measure to get the Fock space, or put another weight. Okay. And people study these things are well studied, but I don't know the results exactly, whether there is a zero product theorem on unbounded domains or not. But yeah, those things have been looked at.
Okay.
So we should slowly move to quotient domains. We start with pseudo reflection groups. So first of all, a pseudo reflection is a matrix, if you like, D by D matrix, which has finite order in GLD, and sigma minus identity. So the I is the identity map on CD that has finite rank. So the sigma, well, after a base change and so on, sigma will essentially look like something like this. Okay, so where omega to the k is 1 for some k. That is a finite order. Okay, so think of sigma as something like this. But of course, this representation will depend on sigma and the basis you are choosing, right? And pseudo reflection group is a finite group generated by pseudo reflections of this kind. So simple examples are finite cyclic groups, symmetric group. The symmetric group is actually a reflection group, right? It's generated by reflection, dihedral and so. Now we'll form the quotient domains, but before that, you take a bounded domain in CD. So remember, omega is a subset of CD, and these are linear maps on CD, right? So any sigma, so if I take Z in sigma, Z in omega, I want sigma Z, which is another point in CD in omega, right? That is all G-invariant means. Then you can form the quotient domain, right? Because you identify the orbits, right? So identify all the points in orbit to one point, you get a quotient domain with quotient topology and so. Well, it is actually a domain, we'll see that soon. Okay. So our aim is to study things on the quotient domain. Okay. So some examples just to some of these are familiar to you. So the most prominent example of a quotient domain is the symmetrized polydisc. So you take the polydisc and symmetrize it. So essentially go modulo the symmetric group action. Okay. So the symmetrized polydisc can actually be written as a domain in CD, which is given by S1Z up to SDZ, where Sj is the jth symmetric function. So what is that? S1 is the first symmetric function. So S1Z is simply first degree polynomial which is symmetric. So Z1 plus Z2 plus etc. Z3. Sj, you can write this as so Sjz would be summation. You take j many of them and then multiply them and then add them up, right? But of course you don't want to add them up twice. So you look at Zi1, Zi2, etc. up to Zij. 1 less than or equal to I1, strictly less than I2, etc. strictly less than Ij, right? So that you are taking j many coordinates and then multiplying. Right? So that is your jth elementary symmetric polynomial. And symmetrized polydisc can be, so G is the symmetric group, then omega by G, where omega is the polydisc, can be realized as this set. Okay. So that is important. Those S1, S2, SD are important. We will see that it's true in general for a pseudo reflection. Then there are Rudin's domains where you go, so G is a finite pseudo reflection group. So it's actually contained in unitary matrices, and so it acts on BD. And
how you are identifying this omega mod G is GD? Or that is.
Oh, well, that's a result. So you will have to, I won't get into the proof of that. Okay. So you will see soon in general this can be done if I have a domain which is G-invariant, omega by G is a domain and can be realized like this. So I wanted to give a specific example. So you will see something like this coming up soon. Similarly, the other domains one studies are Rudin's domains. So these are this is unit ball quotiented with pseudo reflection groups. Rudin was studying proper holomorphic maps from the unit ball to bounded domains in CD, and that is how this came about. Monomial polyhedrons. Okay, so these are, so you take a bunch of monomials and then look at all those sets such that set to the alpha is less than 1. Okay, the alpha can be actually rational, but I'll not get into that. So bunch of, take let's say alpha j equal to 1, 2, 3, etc. some number. These are called monomial polyhedrons. So these are some domains which are actually quotient domains. Okay, so this can monomial polyhedrons can also be realized as quotient domains. So to answer Muna's question, how to realize symmetrized polydisc as a domain, one needs Chevalier-Shepard dot theorem. So this is a purely algebraic result. So you look at polynomials in D variables Z1, Z2, Zd. So that C, Z1, Z2, Zt is the ring of polynomials. And the G on the top says these are G-invariant. Okay, so remember there is a G action on G is after all a D by D matrix, so it acts on CD. And if I take a polynomial, there is a natural action, right? So sigma acting on a polynomial P at the point Z, this is the usual action P of sigma inverse Z, right? So the G invariance here means that sigma P equal to P, right? So you look at all those polynomials which are G invariant. That is equal to polynomials in theta 1, theta 2 up to theta d, where theta I are algebraically independent homogeneous polynomials, if and only if G is a pseudo reflection. Okay, so this is a rather strong theorem. So this is part of invariant theory. It's better to look at the example, which is much easier to understand. If you look at a symmetric polynomial in D variable, that has to be a polynomial in the elementary symmetric polynomials we defined earlier. Okay, so any symmetric polynomial is a polynomial in S1, S2 up to Sd. Okay, so for example, Z1 square plus Z2 square is, so you can look at D equal to 2k. So Z1 square plus Z2 square is a symmetric polynomial, and this can be written as Z1 plus Z2, which is the first symmetric elementary symmetric polynomial, square of that minus 2 times Z1 Z2. Z1 Z2 will be S2, right? So this is S2 and this is S1, right? So this is S1 square minus 2S2, right? It's a polynomial in S1 and S2 in new coordinates S1 and S2 if you like. So any theorem, the CST theorem, Chevalier-Shepard dot theorem, is a generalization of what I just said now for all pseudo reflection groups. Okay, so all the polynomial, any invariant polynomial, any G invariant polynomial is a polynomial in this theta i's. The point is that you have these theta i's. The theta i's are algebraically independent homogeneous polynomials. They are not unique, but their degrees are unique. And well, if you change the thetas, the change is very mild. I'll not get into it. So you get a map.
Sir,
yeah.
What was basically
Yeah.
S2SD? These are S1, S2SD. These are just.
I'm sorry, I'm not able to hear you properly. Can you repeat the question?
What are S1, S2SD?
So I defined the symmetric polynomials in the last slide. Let us go back. Right, the S1 is here. It is only Z1 plus Z2.
Okay.
Right. In two variables, there are only two elementary symmetric ones, Z1 plus Z2 and Z1 Z2.
Okay.
Every other symmetric polynomial in Z1 and Z2 is a polynomial of S1 and S2. Okay. So that is the result we are saying here. That is true in general. That is the Chevalier-Shepard theorem. Okay. The point is you have, instead of S1, S2, you have this theta 1, theta 2 and theta d, which are homogeneous polynomials of certain degrees, and any invariant polynomial, so the G here says that the polynomial is invariant, is a polynomial in theta 1, theta 2, theta d. That means if I take a invariant polynomial is here, so P of Z1 up to Zd will be some polynomial Q in, let's say, theta 1 up to theta d. Right? Theta 1, theta 2 are again functions of Z, right?
So can one say something more about these theta j's in terms of?
Well, they are algebraically independent homogeneous polynomials. Degrees are unique. What else do you want to know?
I mean, like some kind of how does one obtain such? Is there a way of obtaining such?
I see.
Like
how
symmetric group,
obtain?
it is sort of.
How does one obtain? Yeah, I don't know. I haven't looked at the proof of this.
For a finite group, perhaps.
Gargi, if you are there and you know the answer, you can answer. I don't know the answer to this.
Yeah, the proof is not the proof is not constructive. They did not say much about this theta is, but there are results like for some family of groups for which those theta is are identified.
Yeah. So proof is not constructive. And that is expected in general. You can't get anything better than this. But if I give you a G, sometimes it's like finding generators for, let us say, class of differential operators which are invariant at G action and so on, right? So that kind of thing. Yeah.
But one
so
thing
in the
sorry.
Yeah.
But one thing
Go
I
ahead.
want to add that these degrees are very specific. Like these can be the degree can be extracted from the information of the group only.
Okay. So there is more information available. Yeah. Thank you. Now, from our point of view, this map theta, which puts together all the theta i's, is important. So it's called a basic polynomial map associated to G. Okay. So once I give you a G, which is a pseudo reflection group, these theta i's are defined. Okay. And theta i's are defined on the whole CD, right? Because these are homogeneous polynomial maps. And that gives you the domain. Okay. So that is the next result. So the quotient domain. So these are well known. If I take a G-invariant domain where G is a finite pseudo reflection group, it is known that the theta. So from G you get the theta, which is the theta 1, theta 2 up to theta d. You look at the image of omega under theta. That is a domain. So that's a bounded open set in CD. Sorry. And the map is a proper holomorphic map. Moreover, so this is the question which Muna was asking earlier. It is known that omega by G is biholomorphic to theta omega. So one can identify the quotient domain with biholomorphically with a domain theta omega. So in the case of the symmetrized polydisc, the thetas were the S1, S2, SD, right? The elementary symmetric polynomials, and you look at its image, you get the symmetrized polydisc. So our aim is to study Toplitz operators on the Bergman space of these quotient domains. So now I'll not bother about the quotient anymore because it's identified with this guy. So we will look at, so I have some nice domain in CD and I look at the Bergman space over there. Okay, so we need one of the ingredients we need is the analytic version of the CST theorem. So remember the Chevalier-Shepard taught theorem was for polynomials. One can extend it to holomorphic functions, and this was done by 4 people. We'll see their names in the next slide. So just to set up.
I'm sorry, I want to see one more time this Chevalier-Shepard theorem because I am getting some confusion. Homogeneous. These are homogeneous polynomials. That is equal. Okay. Yes.
Okay. All right. So start with the finite pseudo reflection group. I have a bounded domain in G invariant. Now we bring in representation theory of G. So G hat as irreducible representations of equivalence class of irreducible representations of G. G is a finite group. There are only finitely many of them. Now the polynomial ring, so this is all polynomials in Z1, Z2, Zd. There is a G action on that and it decomposes into irreducible, not irreducible, isotypic components, right? So our rho is the rho isotypic component where rho belongs to G hat, right? So you look at all those functions, all those polynomials transforming according to the representation rho. So this is the usual decomposition if you have the action of a group, compact group on a Hilbert space, for example. Here it's just a polynomial. Okay, so among this, if I look at rho to be the trivial one, trivial representation, then our rho is just up to CD G, right? The G invariant. Right? They are the ones which transform according to the trivial representation. But there are other representations as well. And each of these isotypic component is actually a module over the G-invariant polynomials, right? Because if I multiply G-invariant, if I multiply a function, a polynomial from R row, something which transforms according to row with a G-invariant guy, right? So P times Q, where P is G-invariant. So G action on this will not affect P, right? So it's only on Q. So PQ will also transform according to how Q transforms. And so each R row is left invariant under by multiplication by G-invariant polynomials. Now it is known that R row is generated by degree row square homogeneous polynomials. This is part of the Chevalier CST. Okay. And keep this in mind. This is a notation we will use. L rho J. So the rho is the representation. J runs from 1 to degree row square. These are the homogeneous polynomials. Okay. So these are homogeneous polynomials which generate that particular isotypic component. Okay. So just like our trivial, if I look at the trivial one, so that is the invariant ones, then it is generated by those elementary symmetric polynomials, right? Just like that, you have homogeneous polynomials which are I said something wrong. Okay, I'll leave it. So each R row is generated by degree row square homogeneous polynomials, and well, you have much more information about these homogeneous polynomials. Okay, I'll not get into that.
So here,
so
what do you mean by generated by?
Well, so you must. Okay, what do I mean by generated? As a module over that ring. Okay, so just like you generate the vector space. So this works like a basis, but you are able, you can multiply and things like that, right? So any element will be a linear combination of these homogeneous polynomials, but the coefficients will come from that G-invariant polynomials. Okay, so any P in any P in R row can be written as a linear combination of these guys, but except that you can multiply by polynomials which come from invariant ones. Okay. Right, Gargi, that is the correct statement, right? Sometimes I get confused with this algebraic. Yeah.
Yes.
Anyway, we'll see a stronger statement soon. So that is the analytic Chevalier-Shepard theorem, taught theorem. So this was proved very recently by Shivanda Vishwas. I think it is Somnath Datta, Gargi Ghosh, and Subrado, which is to appear in Advances in Mathematics soon. You can do this for holomorphic functions. So any holomorphic function can also be, so yeah, so the before I look at the theorem, so these are the same polynomials we have. Okay, so the CST theorem said things about polynomials. Now we are going to holomorphic function, right? So there is a jump here. Analytic, we are looking at analytic functions. Only thing is now you have G-invariant holomorphic functions, not G-invariant polynomials. So the coefficients are G-invariant holomorphic functions. Okay, so this is a far-reaching generalization of CST. So we'll need this. Again, you may not see exactly where it is used in the proofs, but we still have to reach our results. Now, one of the representations which is very important for our study is this.
The last page, just.
The last slide, is it? Okay.
So that's this. Okay. Yes, sir.
Yeah.
This approach are G invariant, right? And it will.
Sorry?
Approaches are G invariant, right?
Yes. So the G invariant polynomials now have been replaced by G invariant holomorphic functions. Okay, so one of the important representations we need is the Sine representation. So that is defined. So it's a one-dimensional representation. It is determinant of G to the Yeah, I think you need determinant of G to the inverse or just the determinant of G. Anyway, the homogeneous polynomial. So remember, for each representation, there is an isotypic component which is generated by some homogeneous polynomials. Here it is generated by one polynomial, and that is the Jacobian. Jacobian was the theta map. So remember, there is a theta map, which was the basic polynomial map from omega to theta of omega, right? Theta was theta 1 up to theta d, right? The Jacobian of that, so this is the determinant of the complex Jacobian, that is the polynomial which generates the isotypic component with respect to the sign representation. Okay, so just to look at this decomposition. So A2 of omega, so remember this is the Bergman space L2 holomorphic functions on omega. Omega is G invariant, so there is a G action. And if I take a holomorphic function and apply a sigma, I'll still get a holomorphic function, right? It is f of sigma inverse of z, that is holomorphic. So A2 omega is G invariant, and you have a finite group, so it decomposes, right? So you will get these isotypic components, right? The polynomials are sitting inside them. Now, among this, there is one which is the sign representation. Well, there is also the trivial representation, and there are other representations. The sign representation essentially is generated by, so the piece in according to the sign representation. So that is this guy, that is generated by this polynomial Jacobian. So you look at Jacobian times G invariant holomorphic function. That is your A2 sine omega. Okay. And the theorem due to Gargi says that if you look at this map gamma from A2 of theta omega, so now you see this is the quotient domain, Bergman space on the quotient domain. Here you have the original domain. Okay. And a piece of the A2 omega, right? A2 sine omega. That is a, so the gamma is simply you look at f composed with theta. So remember f, where is f? F is from theta omega to c, right? So f composed with theta will be from omega to c, right? So I have omega here. Okay, there is no space here. Okay, so I have omega here. I have theta map here, theta omega here, and I have the function f here. And I have the composition, right? Okay. So f composed with theta, well, it is going to be G invariant. So that's a G invariant function on omega, and you are multiplying by j theta, okay, which is the determinant of the Jacobian, and that is the homogeneous polynomial corresponding to the sign representation. So multiplication takes you to, the theorem says that the multiplication takes you to the isotypic component associated to the sign representation, and it is a unitary map. Okay, so well, here everything is explicit, but one the point that the space on the quotient domain is a piece of the original domain. Okay, that is not very difficult to sort of see or imagine, right? You for example, people working in harmonic analysis, if you look at G by K, L2 of G by K sits inside L2 of G as functions which are K invariant, right? So similar thing is happening here, but the gamma map is very explicit. It is given by multiplication by the Jacobian of the theta map, where theta comes from CST. So as an example, you can look at, so this is the simplest example one can think of. You have D, so this is the polydisc, this is the symmetrized polydisc, and J theta is simply the product of Zi minus Zj. Sorry, any question? Okay. All right, so we go ahead. Now we are coming to the results we have. So zero product theorem. So as I said, we will concentrate on zero product theorem. So maybe I should say a couple of words here about recent works. Well, some years back, well, in a sense, this industry was started by Gadadhar, Subrata and Jankai Sang when they studied, well, when they used the the theta map in the case of the symmetrized polydisc, which is the map which consists of those elementary symmetric polynomials. So write down the reproducing kernel for the Bergman space or weighted Bergman spaces on symmetrized polydisc, right? So using the reproducing kernel on the polydisc, you can write down the reproducing kernel on the symmetrized polydisc, which is the quotient domain. And recently there have been studies of Toplitz operators on symmetrized bidisc and symmetrized polydisc by Tirthankar, Haripado, and Balakrishna Das. Okay, these are very recent, but our results are sort of complement to this in some sense. Okay, so now we can state the zero product theorem. Zero product theorem on the quotient domain. So remember, omega by G is identified with theta omega, where theta is the basic polynomial. So we bounded functions on theta omega. Now you pull it back to to omega. So we always have omega and you have theta omega, right, where theta is. And if I have a function here, let's say C, I can compose it with theta, and you will get u composed with theta. But the point about u composed with theta is, so remember, theta omega is the quotient domain, right? It's omega by G. So if u is a function on omega by G, it is constant on orbits of G. So it is a G-invariant function if you view it as a function on the top domain omega. So these guys, u tilde, so this is the notation we will use, u tilde and v tilde for the pullback function via theta. They are bounded on omega and they are G-invariant. Okay, that is very important. So any function on, so again, for harmonic analysts, any function on G by K is a K-invariant, right K-invariant function on G. Similarly, any function on theta omega is a G-invariant function on omega. Okay, and so you define Toplitz operators on A2 theta omega, just like what we do. You look at a function f, multiply by u, project it back to A2 of theta omega, right? From L2 of theta omega, you project it back to A2 of theta omega, the Bergman space. And similarly, you have Toplitz operators on u tilde or tu tilde and tv tilde on the whole domain, right? A2 of omega. So the zero product theorem, well, the first result, which is abstract enough, was if tu tv equal to 0 on A2 of theta omega, that is the quotient domain, right? If and only if the tu tilde tv tilde is 0 on A2 of omega. Okay, so that is the whole domain, right? A2, the Bergman space over the whole domain. Consequently, if you have zero product theorem on any domain and it is G-invariant, you can form the quotient domain and you can deduce a zero product theorem on the quotient domain. Okay, so zero product theorem on, so in particular for the special case of the polydisc, when omega is polydisc, zero product theorem on the polydisc implies zero product theorem on the symmetrized polydisc. That is the quotient domain, right? So this will be the omega and this is the theta omega. Okay, so let me so sketch of the proof. So I won't get into the technicalities. It will be just 3 points. One is, remember, the A2 omega is G-invariant. So Bergman space is G-invariant. It decomposes into isotypic components. One of them is the trivial representation. So this, the A2 trivial corresponds to the trivial representation. A2 sine represent is the isotypic component associated to the sine representation. And remember the theorem we quoted, Gargi's theorem, which says that A2 sine, that is the component associated to sine representation, can be identified with the Bergman space on the quotient domain. Okay, so the quotient domain sits, the Bergman space of the quotient domain sits inside the Bergman space on the whole domain as a small piece. Now our result says that if you have the product to be 0 on the small piece, it is 0 on the whole space. Okay, so that is the non-trivial part, right? So here the theorem says that it's if and only if one way is trivial, because the product is you sort of project it to one piece, right? So these are orthogonal decomposition. So I have the whole space decomposed into various pieces. And I have something here, and I'm saying that is true in the whole space, right? So from one orthogonal piece, that is A2 sine omega, we are able to go to the whole domain, whole Hilbert space. Okay, that is because when you pull back, you get G-invariance. Okay, so for people who know, if I look at a holomorphic function which is G-invariant, multiplication by that operator, these spaces are reducing subspaces for that multiplication operator. What we are saying is it is true for any L infinity function which is G-invariant. And so TU-TV is 0 on the small domain, or the smaller piece A2 of theta omega implies it is 0 on the full domain via the gamma map. So gamma map, remember, gamma is something which mapped from A2 sine omega to A2 of theta omega, right? So operators here can be pulled back to operators here, okay, via the gamma map. And gamma, you will see that intertwines these Toplitz operators. And if it is 0 on the quotient domain, it will have to be 0 on the sine part of the A2 of omega. And from there, G-invariance implies that it is 0 on the whole domain. Okay, so now in one step, we are going to A2 of omega from A2 of sine. Okay, so this is one of the theorems. You can do this with other one-dimensional representations. I will not get into it. You can study commuting Toplitz operator, and you can get characterizations of commuting Toplitz operators from similar results on omega, and so on. So there are other applications of the fact that gamma sort of acts like a bridge between omega and theta omega. So just to finish, I'll state a specific theorem for the symmetrized polydisc, because that is something which many people are interested in. So remember the result of the 3 Korean mathematicians on the polydisc. Whatever result we have on the polydisc you can push it down to the quotient domain and you will get this result. So this is a corollary. So you start with the function on the quotient domain theta omega, define it to be pluriharmonic if. So remember, we are using the coordinates theta now. So think of phi as a function of thetas, and you look at this. Oh, this should be 0. Sorry, I didn't put the condition. So d square phi by d theta j bar is 0. Then you say G is pluriharmonic. Suppose U and V are bounded G pluriharmonic functions. So these are G pluriharmonic functions on the quotient domain. That is a symmetrized polydisc and continuous. So this is the extra condition you had for the theorem by the 3 Korean mathematicians. GD union W, where W is a relatively open subset of image of the Shilov boundary, right? So theta of TD. So in general, this requires some knowledge about the Shilov boundary, but that is we know this happens. And if TU TV equal to 0 on A2 of GD, that is the symmetrized polydisc, then either U or V equal to 0. Okay, so you have the bounded G pluriharmonic function as the condition. Okay, so I think that is all I want to say. I'll stop with this. Thank you.
Are there any questions?
I have one not so simple question.
Yeah.
Why this group is called pseudo reflection group if sigma minus I identity has rank 1?
Can you repeat? I didn't get the question.
Why the group is called pseudo reflection group if it has finite order and sigma minus identity has rank 1?
I don't know, some problem with the audio. I'm not able to hear you clearly.
He's asking why is it called pseudo reflection group?
Oh, okay. These are sort of generalizations of reflection groups. I don't know if there is any other reason. So reflection groups are groups which are generated by reflections. Reflections have order 2. These are not reflections in that sense, but they share properties of the reflection. For example, they if you choose an appropriate basis, I wrote down the metrics. So there is a huge hyperplane where it acts like an identity, and orthogonal to that hyperplane, it acts like a finite order multiplication by omega. So if that is plus or minus 1, then you get a reflection.
And sir, this projections uses this H2D and L2D.
Yeah.
Sorry, H2D to L2D. Yeah.
L2D to H2D. Yeah.
H2D. This is 1-1 correspondence, or this is
It's
sort of 1-1 correspondence.
It's a projection.
That is
It's a projection. Yeah, it's a projection. So okay, so maybe L2 of, let's say, T. Let's look at that. And so this is all those mod A n square is finite, right? N in Z. The H2 is, you look at, well, if you write it like this, you may not see the difference, but it's like this. It's a half of this. This is sort of, so it's like you look at all those coefficients which are 0 on the negative Fourier coefficients are 0, right? So that sort of sits inside this as a closed
yes. Okay. This is, I am getting sort of confused. Okay, yeah. Now it is clear.
So can I ask something?
Sure.
Now means order 2. That means rho square is equal to identity. So that means you are in group setting and your rho square equal to identity. That means it is involution kind. But if you do not insist upon the range to be full, then you can consider rho cube equal to rho, which means rho is a reflection on the range of rho.
Okay.
So that means rho square on the range of rho is identity on range of rho. And that will come to the algebraic equation rho cube equal to rho. And in terms of generalized inverses, it is that rho is generalized inverse of itself. A reflection is inverse of itself. And this is called trivolution.
Okay.
And there is a long paper by Dagan, which is freely available on the internet, about 30 pages, where trivolutions are studied. So what I would like to know is whether you can move away from group, go away from reflection and consider these trivolutions.
Well, one can consider, but you don't have Chevalier-Shepherd dot. That happens only for pseudo reflection. It's an if and only if condition. So you don't have you don't have generators. So I don't. Our techniques will not work. But one can form quotient domains and study them. But I don't know.
Yes, I know. But what comes to my mind, I must tell. That is it.
Sure.
Because
of course.
The second dual of a group algebra has no reflection. Anti-homomorphism is missing, but it has trivolutions. That is okay. So when you go to algebras, then the reflections are missing, but trivolutions are present.
Thank you.
Very good talk, interesting talk. Thank you very much.
Thank you.
Thank you.
There is a question in the chat also. Can you see?
Oh, chat. Okay. Is the zero product theorem true if? Okay. So if I take more than 2 Toplitz operators, the result is not. It's not known for even for the disk. Over the disk. So our result is simply that if you have results on omega, one can deduce results on omega by G. But as of now, even on the Bergman space over the disk, the general problem of zero product theorem, that if I take finitely many Toplitz operators and if the product is zero, can you conclude that one of the symbols is zero? That is still open.
So, if I'm not wrong here, the Toplitz operator you are considering is for the functions which are invariant under the action of G. That's how
Well, you can say that because the functions, so the function which you pull back from the quotient domain to the original domain is G-invariant.
Yeah.
Yeah. So
what
yeah.
if
So I mean,
have
essentially
functions-
that is the observation one has to make. So the so the decomposition with respect to the G action is respected by the Toplitz operator.
But what if it is not invariant, but it lies in the, for the polynomials you have these irreducible subspaces, right? Where one is the trivial representation. So suppose that function it behaves not, it is not G invariant, but there is some multiple which comes out after the G action.
Yeah. So that okay. So that we don't know. I don't think we have looked at it. So the problem is those functions are not functions on the quotient domain. But as a general question, you can ask that. So the isotypic decomposition you had gives you invariant subspaces for a Toplitz operator where the symbol is not G invariant but transforms according to some representation. Then these are no more invariant under because it will it will shift. So like think of a character. If you multiply two characters, you get another character. You don't go into the same space, right? So for those functions, these spaces will not be invariant. Is that what you're asking?
Mm-hmm.
So okay, maybe I can go to that page.
Yeah, no, I'm asking for those kind of functions. Are there some results like this?
Well, for general functions, bounded functions, there are results, right? So that will be applicable to these functions as well. But I don't know if there are specific results available for such. We get G invariance because we work with the quotient domains. Right? On regular domains, on the full domain, one can take arbitrary functions, arbitrary bounded functions, but D harmonic and some condition, right? So that is fine. There you don't need to assume any property with respect to the G action.
Probably there is no identification of this A2 row gamma unless rho is the sign, right? There is
no. So you can identify all of them in some way or the other.
No, here we are identifying them as elements of A2 theta omega, A2 over some other domain, right?
Yes.
There may not be such a thing, right? Here.
Well, you can. So if I take another representation, you can define a weighted Bergman space on A2 of theta omega. So
So you mean A2 rho omega for rho different from sign, that will be like
yes,
A2 of theta omega with a different weight function.
With a different.
Then there should be a similar theorem, right?
Yes. So so all that. So I chose the minimalist path or whatever, which I didn't want to bring in too many notations. So all this, instead of sign, you can put in any one-dimensional representation, for example. And all the statements we have made is true.
Yeah, you said one-dimensional representation, but
sorry,
you said any irreducible representation of G.
any one-dimensional representation. Yeah. Well, if you take a
Not for any row in G hat.
well, if I take one-dimensional representations, it will be a scalar valued Bergman space, weighted Bergman space on the quotient domain. Otherwise, you should get a vector valued one, but I don't know if we haven't written it down. It's probably true. It's probably contained in Gargi's thesis in some form or the other. Right, Gargi? So did we mention this anywhere?
Sir, actually, yeah, the exact form we did not deduce. For each row, that H row, say the piece denote. So then H row is identified with some reproducing kernel Hilbert space on theta omega, say H row tilde. So that is that identification is there. But for the Bergman space, the thing is we are getting on another weighted Bergman space on theta omega. That has been done for only one dimension.
Only one dimension. Yeah.
What is happening there? Degree of row greater than 1, that is like yet to be
written down. Yeah.
Vector, like tensor product of weighted Bergman space. I don't know.
Yeah. Yeah, so abstractly you can realize any A2 row as a reproducing kernel Hilbert space, vector valued reproducing kernel Hilbert space on the quotient domain. If you want it to be an L2 space, there should be a measure. So that we have done only for one-dimensional representations. Yeah, but I'm more or less sure it is true for any row. One has to find the appropriate weight.
Can I ask one question?
Sure.
Yeah, so this is on the operator theory side. So we know that in classical spaces, we have these algebraic conditions which determine Topless operators. So like, so if we go from theta to the quotient, so will those conditions be changed to?
Can you repeat which conditions?
Like on Hardy space, we have this mz star t, mz equal to t.
Okay. See, that is not known even for the disk, right? Those universal operators, the bilateral shift and the unilateral shift, essentially characterizes Toplitz operators on H2. But that's not true. We see H2, one of the huge differences between H2 of D and A2 of D is that H2 of D is huge in L2. It's half of L2, right? But the moment you come to a domain, the Bergman space is a very small subspace of L2 of D. And there is no result of that kind, right? At least I don't know. There are
some algebraic, by Olafsson or somebody who have deduced some algebraic criteria like that.
Oh, I see. I don't know about those results. Yeah, I don't know. I will be surprised if there are, if you consider everything, I mean, if you consider operators on L2 of D, it would be quite messy. Maybe one has to consider L2 of polyanalytic functions or something like that. There may be some results which are neat or sort of comparable. But I am not aware of those results.
Okay. Thank you.
Are there any further questions? Okay, if not, then let's thank the speaker for a really nice talk.
Thank you.
So I'll stop recording.